Nowadays, autonomous ground vehicles are gaining widespread adoption in the industry, example, factories, warehouses, and occur in everyday applications, example, self-driving cars, restaurants. The main task of these vehicles is the transportation of their load to the goal position. To operate autonomously, the vehicle requires the implementation of a local path planning algorithm, which generates motion commands based on environment information provided by onboard sensors. The pioneering and most popular local path planning algorithm is the artificial potential field. It is based on the interaction of the electrostatic particles given by the following formula, where K is the interactions constant, Q1 and Q2 are the electric charges of the particles, and R is the distance between the particles. To provide the collision-free and goal-reaching path, the obstacles and autonomous vehicles are assumed to have the same charge, and the goal position is the opposite charge particle. In such a case, the obstacle generates repulsive force, and the goal position generates attractive force. The overall force applied to the autonomous vehicle is equal to the sum of repulsive and attractive forces. The vehicle's next direction and linear velocity can be calculated using the obtained force. The algorithm allows obtaining a collision-free path to the goal in an unknown environment. Unfortunately, the artificial potential field algorithm has a few problems. The first one is no mechanism of avoiding or bypassing the dead ends. In the case of a vehicle going into, it cannot get out without human intervention or another mechanism. In very narrow passages, the repulsive force generated by the walls can stop the robot from getting between them. In this situation, the goal will not be reached. The artificial potential field algorithm generates an oscillation in the presence of obstacles, which is mainly related to the limited dynamics of the vehicle. The obtained orientation and linear velocity from the algorithm are set as reference values to the motion controller of the vehicle, and an additional time is required to obtain proper orientation and speed. The same situation occurs in narrow corridors. It should be noted that the oscillations can be unstable and eventually provide to the collision. In the predictive artificial potential field algorithm, the smoothness of the vehicle's movement and energy efficiency has been taken into account. The steps of the predictive algorithm are summarized in this slide. On its right side, the example environment is presented. Firstly, we create a direction line as a force direction obtained by the original artificial potential field algorithm. Next, the obtained force is used to predict a future position of the vehicle by using a constant step size to obtain direction. The process is repeated the predefined number of times to obtain the predicted trajectory of the vehicle. For each predicted point, the distance between it and the direction line is calculated. To allow the vehicle to react in advance to the obstacle, the farthest point from the direction line is selected as a new temporary goal. The selected point is used as a goal position to calculate the artificial potential field force. Due to this, the vehicle can react to the obstacle before the original algorithm, and the orientation of the movement is changing smoothly. Furthermore, the path obtained by the predictive artificial potential field generates a much shorter path. All these advantages reduce energy consumption. The validation of the proposed predictive-based path planning algorithm was made using the Husarian ROS Bot 2.0 Pro mobile robot and robot operating system. The original artificial potential field algorithm and predictive one were implemented in C++ programming language, and they are based only on the LiDAR sensor. The horizon of prediction value should be selected considering the vehicle, environment, and assumed obstacles dimensions, but also the use sensor and vehicle's perception. The longer path is predicted, then the vehicle will react in advance to the obstacle, but if the predicted path is too long, then the prediction may be generated without information about the environment behind the obstacle and may provide an imprecise prediction of future movements in a complex environment. One can see that a longer horizon of prediction provides a smoother and shorter path. For horizon of prediction equal to 2 meters, and unsmooth movement occurs, which was caused by above-mentioned inaccurate prediction in long horizon due to lack of perception behind the obstacle. Analyzing the size of the Husarian ROSPOT 2.0 Pro and the available environment, the authors selected a horizon of prediction equal to 1 meter for subsequent examinations. This value provides a significantly smoother and shorter path. Now, additional 2 examinations will be presented. The first one, called Test 1, has only one obstacle to present the simple example, where the analysis and comparison of the proposed approach and the original one are simplified. The second environment, Test 2, has been used to evaluate the algorithm in case of 2 obstacles very close to each other with a narrow gap between the mobile robot. The Predictive Artificial Potential Field algorithm provides a much smoother path. The predicted trajectory successfully gives the information about the new temporary point, and the goal position is reached faster than the original algorithm. In Test 2, the Predictive Artificial Potential Field presents that even in a narrow gap, the algorithm provides an oscillation-free movement, and still the traveled path in comparison to the original algorithm in that part of the environment is much smoother. The indicators presented in table prove the efficiency of the Predictive Artificial Potential Field algorithm. The time required to reach the goal is around 10% shorter than the original algorithm, and also, the traveled path is significantly shorter by 4.4% and 8.73% for Test 1 and Test 2, respectively. To provide higher accuracy of efficiency measurements, each experiment was performed 3 times. The goal was 10 meters in front of the robot, and 3 obstacles were placed in the path, similar to the setup horizon of the prediction environment. The application of the proposed PAPF allowed to reduce the used electric power by 32.1 mAh, which is 21.4%.